Problem sheet 5, question 3. Consider the following linear programming problem. Maximize 3x1 plus x2 plus 3x3 subject to x1 minus x2 plus 4x3 is less than 17, 2x1 plus x3 is less than or equal to 6, 2x2 plus 3x3 is less than or equal to 14, and all the variables are non-negative. First, use the simplex method to find one optimal solution. Then pivot one more time to find all optimal solutions and give your answer in a particular form. So there must be non-unique solutions here. And see, if we fix x3 is equal to 1, find the values x1 and x2 must take for the solution to remain optimal. Okay, first let's write this in standard form. So we will maximize subject to So in standard form, we have all our constraints as equalities and we've introduced 3 slack variables. Once we have this, we can write down our initial simplex tableau to start the simplex algorithm. This is a maximization problem, so we will write down our objective row with the negative of the coefficients. The initial simplex tableau always begins with x1, x2, x3 is equal to 0. That would result in an objective value of 0. Now our first iteration, we're going to perform row operations on this in order to try and aim to get our objective row full of non-negative coefficients. So we want to choose our work column as that with the most negative value in the objective row. Now there are potentially 2 of these. Now we're going to find our pivot by dividing the left-hand side by the work column and choosing the element that results in the least positive ratio. So we have 17 over 1, 6 over 2, 14 over 0, 17 over 4, 6 over 1, 14 over 3. And the least positive there will be 6 over 2. So that'll give us this is our pivot. And so we know which column is our work column. The row operations, we want to make our work column 0, 1, 0, 0. So that'll be our new row 2 would be half our old row 2. Our new row 1 will be row 1 minus our new row 2. Our new row 3 does not need to change. Our new row 4 is going to be row 4 plus 3 lots of our new row 2. We can perform those row operations. We'll repeat the process now in our second iteration. So we will choose our column with the value in the objective row that's the most negative. That's the x3 column. And we will choose our pivot to be the element in that work column. When we divide the left-hand side by that column, gives us the least positive ratio. 14 divided by 7 over 2 is 4. 3 divided by half is 6. 14 divided by 3 is 4 2/3, and so this is our pivot. Again, we want to choose row operations so that the x3 column becomes 1, 0, 0, 0. So we can choose our new R1 becomes 2 over 7 times our old R1. Our new R2 becomes R2 minus a half our new R1. R3 becomes our old R3 minus 3 lots of our new R1, and R4 becomes our old R4 plus 3 over 2 lots of our new R1. And we can perform those row operations to get the next tableau in the iteration. After this iteration, we still have a negative value in the objective row, and so we have to pivot one more time. So let's choose our work column to be the column with the most negative value in the objective row. And we choose our pivot to be the element when we divide the left-hand side by it gives us the least positive ratio. So 4 divided by minus 2 over 7 gives us something negative. 1 divided by a seventh is 7. 2 divided by 20 over 7 is 7 over 10. So the least positive here. So we need to decide on our row operations. So we want to get this column to be 0, 0, 1, 0. So our new R3 will be 7 over 20 R3. Our new R1 will be our old R1 plus 2 over 7, our new R3. Our new R2 will be our old R2 minus a seventh, our new R3. And our new R4 will be our old R4 plus 10 over 7, our new R3. We can perform those row operations. And now we have no negative values in our objective row anymore, so we have found one optimal solution. We can read off that optimal solution by looking at our basic variables. Those are the ones with zeros and ones in the columns, so x1, x2 and x3, and we read them off by going down to the 1 and over to the left hand side. So that gives us x1 is equal to 9/10, x2 is equal to 7/10, and x3 is equal to 21 over 5, giving an objective value of 16. Part B asks, pivot one more time to find all optimal solutions and give your answer in a specific form. So how can we pivot one more time? Well, we have a non-basic variable, S1, that has a 0 in its objective row. That means we could pivot on this column. What does pivoting mean? That means we want this to be all zeros and 1, 1. Now there's already a 0 in the objective row, so the objective row would not be affected by this. And so this would just bring us to another tableau with no negative values in the objective row, and so we'd have another tableau that represents another solution. So we are able to do that. So in order to choose the pivot here, we have to choose a fifth as our pivot because the other values would give us a negative ratio. And we can choose our row operations. So in this case, we could choose our new R1 to be 5 lots of our old R1. We could choose our new R2 to be our old R2 plus a tenth of our new R1. Our new R3 would be our old R3 plus 3/10 of our new R1. And we do not need to change R4, so there's already a 0 there. So our new R4 will just be our old R4. Performing these row operations, we will get this gives us a new optimal solution that we can read off as x1 is equal to 3, x2 is equal to 7, x3 is non-basic, so that would be set to 0, and that still gives us an objective value of 16. So these are two solutions that give us the same objective value, so these are equivalent and that we know these are both optimal. Now you can check if we were to pivot again, what would happen. We would take the column that is non-basic with a 0 in the objective row. That would be x3, so we would pivot here, and that would eventually make x3 basic again, and we would jump back to this tableau and we just alternate between the two. So these two are both optimal solutions. We also know that all points on the line segment between these 2 points are also optimal, which is why the question is asking, write down the set of all optimal solutions as a line segment. So the question asked for the set to look like this, where the vectors A and B are our 2 solutions that we found. Our first solution, let's call that A, was that x1 was 9 over 10, x2 7 over 10, and x3 21 over 5. And our second solution, B, that we found by pivoting again, gave us that x1 was equal to 3, x2 is 7, and x3 was 0. We can therefore write our set of optimal solutions as 1 minus t times 9 tenths, 7 tenths, 21 fifths, plus t lot of 3, 7, 0. Part C then asked, if we fix x3 is equal to 1, what values must x1 and x2 take for the solution to remain optimal? Now, x3 equals to 1, that would lie on the segment we have here, because x3 can take any value from 0 to 21 over 5. So we can fix x3 equals to 1. But in terms of our parameter t, which represents how far along the line segment we are, what does that correspond to? Well, x3 here corresponds to 1 minus t times 21 over 5 plus 0 times t. So we have the equation 1 is equal to 21 over 5 minus 21 over 5t. We can solve this and get 21 over 5t is equal to 21 over 5 minus 1, which is equal to 16 over 5. So then we have t is equal to 16 over 5 divided by 21 over 5, which is 16 over 21. We double check, our t has to lie between 0 and 1, and it does. So we have a value t is equal to 16 over 21, corresponds with x3 is equal to 1. Now, if this is the case, what must the other values take? x1 and x2 must then correspond to whatever this formula gives us when t is equal to 16 over 21. So we can say that x1, according to this formula, would be 1 minus t times 9 over 10 plus 3t, and x2 would be 1 minus t times 7 over 10 plus 7t. And when t is equal to 16 over 21, these would correspond to x1 is 5 over 2, x2 is 11 over 2, and of course we know that x1 is fixed at 1. And you can double check that in the objective function that still gives us the optimal value of 16. So our objective function here was maximize 3x1 plus x2 plus 3x3, which would correspond to 3 multiplied by 5 over 2 plus 11 over 2 plus 3 multiplied by 1, giving 15 over 2 plus 11 over 2 plus 3, which does indeed give 16. And so the solution remains optimal. It's just not a basic solution anymore, but it's still an optimal solution.